I guess this is it, right? This is our last lecture of the quarter. Okay. Today we're gonna sort of finish our discussion of these systems of equations and the matrices that we can use to represent them and all of that, and have a little chat about this concept that came up on Tuesday called the determinant. Okay. And we've already seen the determinant of a 2 by 2. The determinant of a 1 by 1 matrix, right? A 1 by 1 matrix is just a single number in a matrix. The determinant of a 1 by 1 is just that number, right? Um, and we sort of alluded to this on Tuesday, okay? That the determinant of a 2 by 2 matrix, we'll go A equals A, B, C, D, okay, is, and there's two ways that we can write it, okay? The first one is DET, and then parentheses, our matrix. And the other one is, you know how we always use these brackets to surround our matrix? Well, if we surround it with straight lines, sort of like an absolute value, right? You can also write it, like I said, around the whole matrix itself. That is also a way to represent the action of taking the determinant of this matrix. And for a 2 by 2, it's going to be AD minus CB. Okay. Notice that that's multiplying down this diagonal and subtracting that. Okay. So we can do an example of this. Let's consider the following matrix. We'll go 6, -3, 2, and 3. Okay. And let's take the determinant of this guy. Well, that's going to be 6 times 3 minus 2 times -3, right? Which looks like to me that's going to be 18 plus 6, or 24. Okay. For these 2 by 2s, it's not particularly difficult to calculate. You just need to remember, you multiply that and then you subtract that. Okay. And I'm going to give you a theorem now, and that's going to sort of tell us why we care about this determinant. Okay. And similar to some of the theorems we discussed on Tuesday, this isn't one that we can prove with the tools from pre-calculus. We get it from another area of math. But, despite us not being able to prove it in this class, it is indeed true that a matrix, call it A, is invertible. Okay, where it's invertible means we can find its inverse, right? If and only if the determinant of A does not equal 0, okay? So this says that if our matrix has an inverse, then its determinant can't be 0, right? And that's really, really useful, right? Because then we can, before even trying to find an inverse to our system, we can calculate the determinant of the coefficient matrix, and that will tell us whether or not we have a solution in the first place, okay? So before we kind of go on to talk about determinants of higher matrices, one of the natural questions that might arise is the following, right? So if one of these 2 by 2 matrices, A, B, C, D, is not invertible, then what should we expect it to look like? right? Can we quickly at a glance figure out a pattern when A, B, C, D is not invertible, right? Well, if it's not invertible, then its determinant is 0. So then AD minus CB equals 0, right? Which that implies that A times D equals C times B, okay? So what that directly gives us, okay, is the following. We're going to have A and B here, okay? This relationship here tells us that our bottom row needs to be a multiple of the top row, right? Because whenever we do this product, we need to get the same thing as this product. So what that means is that there's some fixed real number k such that that's true, okay? And that's how we can immediately recognize that our 2 by 2 matrix is going to have 0 determinant, right? If we were, say, taking the determinant of, let's manufacture one of these guys. Let's say 2, 3, and then we'll multiply by 2, right? We'll go 4 and 6. Well, when I do this determinant, we're going to have 2 times 6 minus 4 times 3, both of which equal 12, so we are indeed at 0, okay? So the next natural thing that we do want to do is find the determinant of, some sort of arbitrary n by n matrix, okay? But there's two sort of things that we need to look at first, okay? And those are called minors and cofactors, okay? So here's our setup for this. Let's say n be an n by n matrix, and we'll define a couple of things. And our first one, okay, is the minor, which we call m sub ij, okay? This is of the element aij. Okay, so if you pick some aij, its minor is mij. Okay, I guess I'll highlight that. But what is it? It's the determinant of the matrix obtained by, so we're gonna delete, okay, the ith row and the jth column of that original matrix, okay? And then our second thing to define, and then of course we'll get some examples of how these things work, is the cofactor of aij, right? One of these elements is, let's go down here. So it's capital A sub ij, okay? It's going to be -1 to the power of I plus j times the minor of this element ij, okay? So I know that that's strange, and these will, directly come up and show us how to compute determinants. But let's take a look at first at these concepts of minors and cofactors, okay? And to do that, we'll need a matrix. So let's grab this matrix. Let's try 2, 3, -1, 0, 2, 4, and -2, 5, 6, okay? Let's start by looking at m sub 1, 2. Okay? So according to our definition, this is the determinant of the matrix obtained by deleting the ith row and the jth column. So this is asking us to delete the first row and the second column. Okay? Well, if I delete the first row, it's going to cross out those elements. And if I delete the first column, or the second column, it's going to leave us with those elements. Okay? And so we're taking the determinant of the matrix left over. Okay? So what's left over? It looks like we have 0, 4, -2, and 6. So when we take the determinant of that, well, it looks like we're going to get 0 minus a -8 for 0 plus 8 for 8. Okay. What about the cofactor of, say, 1, 2, right? Well, it's going to be -1 to the 1 plus 2 times the 1, 2 minor. So -1 cubed is -1 times 8 is -8. Okay, let's try one more of these. And how about we do the 3, 3 minor? Okay, it's going to involve deleting the third row and the third column. So it looks like the matrix that we're left with is 2, 3, 0, 2. Okay. And when we take the determinant of that, looks like we're going to have 4 minus 3 times 0, so minus 0, which is just 4. And then what is our cofactor going to be? Well, our cofactor, a sub 3, 3, is going to be -1 to the 3 plus 3, okay, times the 3, 3 minor. Well, 3 plus 3 is 6, so -1 to the 6th is just going to be 1. So we're left with 4. One thing that might be of use for you is noticing the pattern that comes from this like sign that goes before our cofactors. Okay. Right, because that's independent of the elements in the matrix, right? It's just based on the structure of the matrix itself, right? Our 1, 1 element is going to be -1 to the 2, right? But then notice, when I step one entry this way, right, my row stays the same, but my column increases, right? Or if I step an element this way, my column stays the same, but my row increases by 1. So that means that every step you change the sign, which is going to end up with this nice checkerboard pattern, just like this, right? And I'm sure that if you think just a little bit, you could figure out what happens, in some arbitrary sized square matrix using a very similar argument, okay? So I would recommend, thinking about this sort of pattern and make sure that you can use it well to expand out all of these cofactors, because these cofactors will be how we calculate the determinant of our matrices. Okay, so let's write down a definition. Okay, so if we have A is an n by n matrix, right, so some nice square matrix, then we calculate the determinant of A with, and I'll just write DET here. So the first thing we'll need is a big matrix, right? So we'll have A11, A12 all the way. AN2, And here we have A, N, N, okay? So that's our matrix, okay? And here's what the determinant equals, okay? We obtained the determinant by multiplying each element in the first row by its cofactor and then adding the results, okay? So what that means is we're going to take A11, little a11, right, this element, and we're going to multiply it by its cofactor, right? Well, remember, this cofactor is the determinant of this matrix that's left over multiplied by either 1 or minus 1, okay? So we're going to do that for A11, then we're going to take A12, multiply it by its cofactor, right, where you find that cofactor by removing this row and this column, taking the determinant and then multiplying by the proper sign. And then we're going to do the same thing to A13 times its cofactor all the way to A1n times big A1n, okay? So this is how you do it, right? You split it up into smaller determinants. When you're finding the determinant of a 3 by 3, as we'll see in a second, it's going to turn into the determinant of a bunch of 2 by 2s, right? Because when you remove a row and a column from a 3 by 3, you get a 2 by 2. But this is actually defined recursively, right? If we have, you know, some n by n matrix like this, right? Notice that each of these cofactors involves the determinant of an n minus 1 by n minus 1 matrix. So when you're taking the determinant of this, you'll have to expand it out. Eventually, these will all get down to 2 by 2 matrices, and you'll be able to calculate them with, the sort of simple multiply one way, multiply the other way method, okay? So let's take a look at an example, okay? Let's calculate the determinant of 2, 3, negative 1, 0, 2, 4, negative 2, 5, 6. Okay. If this matrix looks a little familiar, there's probably a reason for that. Okay. But if we want to calculate this determinant, what's going to happen? Okay. We're going to start with our first element, 2, and we're going to multiply by its cofactor, right? Which is going to be negative 1 to the 1 plus 1 times the determinant of the matrix that we find by removing this and this, right? So that looks like it's going to be 2, 4, 5, 6. 2, 4, 5, 6. Okay? And then what? Well, we're going to add 3 times it looks like negative 1 to the 1 plus 2, right? And then that's going to get multiplied by the leftovers from this. So 0, 4, negative 2, 6. And I guess we'll move this down here for the sake of room. Because what's going to happen next? Well, we're going to have negative 1 times negative 1 to that looks like 1 plus 3, right? Times the determinant of what? Well, we're going to remove this and that. So it looks like we're going to have 0, 2, negative 2, 5. Okay. So now as we simplify this, what happens? Well, we get, it looks like 2 times 12 minus 20 minus 3 times, looks like 0 plus 8 plus negative 1 times 4. Okay. So that looks like to me it's going to be minus 16 minus 24 minus 4 equals negative 44. So the determinant of this matrix is negative 44. And that means that it's not 0, so it therefore must have an inverse, okay? One thing that I think it's useful for us to notice, okay, is that when we defined the determinant, we said that you need to sort of do this expansion process on the first row. And that's not entirely true. Going across the first row always works, right? But in fact, you can follow this expansion on any row or any column, okay? Now, we're not going to prove it, unfortunately, but it is worth noting that if there's another column or another row that it would be easier to expand on, absolutely go there, right? Because it's a quicker process. It's going to, maybe not admit as many mistakes, right? So let's, for example, take a look at this guy again, okay? Why don't we write a 6 right there? But why don't we try expanding on the second column and see what happens, right? Before we expand on the second column, I'm going to write in this guy, just so that we can ignore the -1 to the whatever and just use these, right? So the cofactor of this element is going to be negative. The cofactor of this element is going to be positive, right? That's how we can use this table, okay? So if we're expanding on the second row, what's going to happen? Well, we're going to have, I guess, -0 times what? Well, that's going to go away and that's going to go away. So it's going to be 3, -1, 5, 6. Then we're going to have +2 times what happens when we remove those. Well, it looks like it's going to be 2, -1, -2, 6. So 2, -1, -2, 6. And then if we expand on our last one, I guess each of these should be determinants. If we expand on our last one, it's going to be 4 times 2, 3, -2, 5. Okay. But here's the nice thing about choosing to expand on this row, is that this 0 right here, well, that's just going to cancel out all of that, right? So that means we have less to work with computationally. Looks like we're going to have 2. Well, we're going to have times 12 minus 2, so 2 times 10. Then we're going to subtract from that 4 times what we have 2 times 10 times what we have 2 times 5 for 10 minus 6 minus a -6 for +6, right? So that looks like it's going to be 20 minus 64, which is indeed -44, just like we showed right here. So again, we can't prove this using the tools from our course, but you can prove that it doesn't matter which row or column you expand on, you're always going to end up with the determinant, okay? And then a moment for you to kind of pause, take a, get a snack or whatever, but then go ahead and try expanding this on the third column and make sure that you get -44 and that you're comfortable with this determinant process, okay? So let's take a look at another example, okay? So let's say show the following matrix is singular. Okay. So let's take a look at this matrix. We'll say 1, 2, 0, 4. So if you'll notice, this guy is going to be 5, 6, 2, 6. This is going to be a 4 by 4. Okay. But one of the nice things about this 4 by 4 matrix is this row right here. Okay. Because if you remember, a matrix is singular when it is not invertible, right? Generally in mathematics, if you ever hear something called singular, it's not great. Usually it has some sort of distinguished property, but it's not the kind of property that we generally want, right? So in this case, we want matrices to be invertible. Singular matrices are not. And how can we show that a matrix is not invertible? Well, we can simply take its determinant, okay? And we could expand on the first row. We could expand on the third column. But this is where picking our rows and columns that we want to expand on well saves us just a ton of work, right? Look at what happens if we expand on the third column, or the second row, okay? If we expand on the second row, we're going to get 0 times a21 plus 0 times a22 plus 0 times a23 plus 3 times a24. So everything drops out, and our determinant turns into this. It turns into 3 times, well, what happens when I remove this row and this column? Well, the matrix left over is 1, 2, 0. Looks like 5, 6, 2, 2, 4, 0, right? And we have 2 plus 4 is 6, so our -1 factor is -1 to the 6th, so it's just going to be +3, okay? But now we would need to calculate this. And once again, we can expand on any row or column that we want. So why don't we expand on column 3, right? Because if we expand on column 3, we're going to have 0 times its cofactor plus 2 times its cofactor plus 0 times its cofactor, right? So all that's left is we're going to have 3 times 2 times the cofactor. But what's our cofactor here? Well, this is what? This is the second row in the third column, so we are going to have a factor of -1, right? Times what? Well, what's left over? We're going to have 1, 2, 2, 4, right? So then what happens there? We can combine our -1, our 2, and our 3 for a -6 times this smaller determinant, right? Through carefully picking our rows and columns, we've turned a 4 by 4 determinant into a 2 by 2 determinant, right? So what are we going to get? Well, we're going to get -6 times 4 minus 4, which is indeed 0, exactly what we wanted, right? Because we wanted to show that our matrix is singular. Perfect. Okay. There's one last little thing that I want to show you guys. We're not going to prove it in the lecture. One of the exercises in the book, it's not one that I'm going to assign for homework or anything, but exercise 74 in section 10.6 asks you to prove what I'm about to show you works. And it is a cool and interesting proof. So if you're curious about how this works, definitely go through that. But let's say we have some triangle in the plane, right? These are our xy axes, and we have some triangle, right? If it's some triangle, it's going to need some points, right? So let's label them. I don't know. We'll call this one A1, B1, right? Let's say we'll call this one A2, B2, and we'll call this guy, I don't know, maybe A3, B3, okay? And we can actually, believe it or not, compute the area of this triangle with a determinant. And I guess I'll rearrange that guy, okay? So if we're looking for this guy, right, say, let's call him Fancy A, okay, for the area of this, okay? Well, it turns out that this is how you can calculate your area, okay? Your Fancy A, well, it's equal to plus or minus 1/2 times the determinant. We write A1, B1, 1, A2, B2, 1, and A3, B3, 1. Okay, where you choose this sign to make this positive, right? If this determinant ends up negative, you choose negative 1/2. If it ends up positive, you go positive, okay? So let's do one quick example of this, and then that will actually, that will wrap up our course. So I guess we'll need a triangle then, right? So let's say our vertices, we'll put one at 1, 2. We'll put the next one at 3, 6. And we'll put the third one at, say, -1, and then up 1, 2, 3, 4. Okay? So this is our triangle. And we're interested in finding its area. Okay? So what's our area going to be? Okay? Where I guess this is just one of the other fancy A's that you can draw. Okay? So what's our area? It's going to be plus or minus 1/2 times what determinant? Well, what are our coordinates, right? We're going to have 1, 2, we said 3, 6, and we said -1, 4, and then a column of 1s, okay? Why don't we expand along the, we'll expand along the first row, okay? So we're going to have plus or minus 1/2 times what? Well, we're going to have 1 times its cofactor, which is going to be 6, 1, 4, 1. I'm going to do -2, it looks like times 3, 1, -1, 1. And then plus 1 times 3, 6, -1, 4. Where again, we find these by deleting a given row and column and looking at what's left over, okay? So if we simplify this, we're still left with plus or minus 1/2. We're going to have 1 times 6 minus 4, or 2. We're going to have -2, it looks like, times 3 plus 1, right? So -2 times 3 plus 1 is going to be -2 times 4 for a total of a -8. And then we're going to have 1, looks like we're going to have 12 here plus 6 here for a total of 18. Okay, so then adding those up, we're going to have still plus or minus 1/2, looks like times 12. Okay, and so we should choose plus 1/2 so that our area does not go negative, right? Because it doesn't make any sense ever to have negative area, okay? And that's going to say that my area is 6, whatever our units are, squared, okay? And with this last little application of the determinant, that's going to wrap up all of the official instruction for this course. So it has been an honor to teach y'all and see you during office hours and all that. So best of luck on the final next week. And if you need anything at all, shoot me an email.